Thank you very much, and good to be here. It's great to be here. I thank you very much for giving me the opportunity to talk a little bit about research that we have been doing during the last decades on shallow groundwater temperatures, and I, of course, will also give you a little bit of insight in some fundamentals. So the focus is on these four different themes. We are interested in how temperatures evolve in the subsurface, and once again focuses on the shallow subsurface, which makes life a little bit easy if you do not consider so much the extreme conditions, but those which are typically happening in shallow groundwater. So that means something like a depth of 100 meters. And in this depth, for example, we don't have normally free convection. The parameters to describe these conditions and which are most sensitive are those which we are familiar with and which are mostly the hydraulic parameters. Shallow groundwater conditions are here in the focus at local scale, at global scale, and it's not just the shallow groundwater at some measurement points, but it's especially the question of how groundwater changes in space, in time, and groundwater, especially in urban areas, is very interesting with respect to the thermal conditions. And finally, of course, we are interested in why we're doing that, and I would like to also show some implications why this is relevant. These four different themes, they are kind of my guiding points, but at the same time, I have to say that the slides are a little bit mixed, so the order will be a little bit different, but finally I think we all find our way. So the overarching title today is that temperature is a critical variable. And you may ask ChatGPT why this is like this. And we find, I think this was one answer which I slightly modified and adopted a little bit to our conditions. But it's not bad, because it seems like it makes sense that temperatures are super relevant for assessing how heat is moving. Temperature is an indicator for us for the question of how much energy is there in the ground, which is elementary for judging if the ground can be used for geothermal use. Of course, many of you work on chemical transport and reactions, and they are all triggered and influenced by thermal conditions, and not just the chemical reactions, but especially also microbial activities. And finally, that also links to the elementary role of temperature for life, which may be sometimes a critical variable. Okay, so as I said, so we are here not diving very deep in the ground and also not in the methods that we are using, and we can rely on a few principles, and most important is to understand which kind of processes are most relevant. And I guess many of you heard once upon their time about conduction, and conduction is usually described in a similar way as solute diffusion is described with the Fick's law. You can describe the heat transport by conduction, the diffusive heat transport by Fourier's law. And looks similar. The heat flux in watt per square meter, which is this one here, is a function of the temperature gradient and some lambda. And the lambda is the thermal conductivity as a parameter which is a little bit temperature dependent, but usually we ignore that. We can also, if you look at this here as a one-dimensional perspective, we can also consider in one dimension, but also in three dimensions, of course, the conductive heat transport, and describe it in the same way as we would do it in, I think, Fick's second law for solute transport. And then we have an equation which sounds familiar, and I guess has been on the board already very early. It looks always the same. Finally, the change in temperature in time and in space is mostly controlled here according to this equation by another parameter, which is the thermal diffusivity, The thermal diffusivity is not a new parameter because it's a ratio between the thermal conductivity and the heat capacity. Now, how does it relate to each other? Thermal conductivity is a measure how much energy, how much heat is released or is propagating through some media. And the thermal diffusivity tells us how fast a temperature signal moves through some media. So this is a little bit different. Okay. So if we have this equation, I'm showing this one here because this is the one which is sufficient for my studies, actually. If we have that, we can use standard procedures to get some analytical solution. For example, when we assume some semi-infinite space, 1D, and we have, and this is something we use, semi-infinite space, especially for the ground surface. And we are interested in how temperature variations at the ground surface influence the deeper subsurface. In order to judge that, we have such complementary error function based equation which can be superimposed, and by this we can, for example, as a condition, as a boundary condition, we can assign temperature trends very easily and superimpose such equations and do not need any numerical method.
So this is for zero velocity?
Zero groundwater velocity. This can also be, there are also extensions which also include advection. Advection, next thing to look at, but before this, because these parameters are relevant, let's have a closer look. Thermal conductivity and heat capacity, these two primary parameters are usually not very variable, or in other words, they tend to be parameters which you can judge very well, because usually you know what rock you're dealing with, you have some guess about the porosity, if you know full saturations. I imagine that you're pretty safe in estimating the values. When it becomes a little bit more complex is when we have unsaturated conditions in water, partial water saturation here involved. And this is just one example where the dependency, for example, of the thermal conductivity on the water saturation for different soil types is shown. Still, the variability is not enormous, it's not high, but it's changing. And why? Because water, of course, is a much better conductor than, in this case, air. And also heat capacity of water is very high. If we take the ratio of these, we have the thermal diffusivity, and the thermal diffusivity as a consequence is not any linear or some uniform kind of trend that you find. Usually it goes up and down. So the thermal diffusivity obviously is controlled by both of these parameters, and that's why the water saturation, for example, does not influence strongly some one directional trend of the thermal diffusivity. So we have here very easy ingredients to describe the heat conduction. If we want to find some very simple way to calculate how much the contribution by groundwater flow or advection or convection is, one way, for example, would be if we have some specific discharge, the heat capacity of water, and some temperature difference between an inlet and outlet of water, which, for example, goes through some porous media, we can calculate here also the contribution by the convective heat flux. And for such conditions, not just in 2D but also 3D, we could calculate also a thermal Peckley number. So all these kind of pieces that we are familiar with. So that's all the secret. So I could stop here. At least for my purpose, this is enough of basic knowledge that I need. And for extending this basic knowledge and refreshing what you maybe know already, I'm asking you, what do you think? How much energy is in a rock? With all these knowledge, and how would you calculate that? And we assumed this could be, for example, maybe not to size, but this is big granite of 1 kilometer, and so we are diving deep in the ground. We think of deep geothermal applications. You're an engineer now, you have to judge how much energy is there, how much energy do I get out? And we have some settings here. We assume that we can decrease the temperature, let it be 150 degrees Celsius. We decrease the temperature by 20 Kelvin or 20 degrees Celsius. So 1 cubic kilometer, very easy. The volume, we have a heat capacity, we look up in the textbook how much that could be, and we have a temperature difference. And this way we end up with some value, which is usually very high for energy. In this case, 5 times 10 to the power 16 joules, which is hard to understand what that means. But if we assume very roughly that there's a geothermal plant operating and has an efficiency of something like 10-13% in order to transfer this heat into some power, and this is pretty, I would say, normal range, so about 10% of the original heat can be transformed with deep geothermal plants into electricity. This is the capacity you would have with this power plant to sustain 20 years. This is a lot. It's a lot because this is not a big plant, it's a small plant, but it's a lot. It's a lot of energy considering how many of these big blocks are there in the ground. Should be sufficient for Corsica and for, I guess, the rest of the world if life would be so simple. It's not so simple. Why? What do you think is the next question or next slide? It's a little bit obvious what is missing here. The big question is, if you compare what we have calculated before, which was the heat in place, a term which is frequently used, like how much energy is there, we ask now the question, how do we get it out? And once again, we use these simple procedures. And in this case, I try to make it super simple. Let's assume in our big granite, we have some vertical fracture. So some engineered geothermal system may be implemented and whatsoever. But finally, we have some vertical fracture. We assume everything is super simplified. We have some thermal gradient here from the left to the right, and it's only 1D as a proxy. And this is like this gradient is not evolving, it's just like a steady state condition. So if you take this, and once again, what we have learned before, we look up some thermal conductivity, we have the cross section, we need it from both sides, heat flux, and we have the thermal gradient. So what do you expect? Of course, not so much. If you look at the value which finally is obtained, it's actually very little. I guess it's the power of the van which takes us to the airport and back. So this is the bad news actually. There's a lot of energy, but don't get it out. So maybe that paves a little the path to the speech after mine, because this is mainly, I guess, on, we have not talked to each other. I guess it's more focused on deep geothermal and the question of how to use that. Finally, when we deal with geothermal conditions, we're always in trouble of the question, how do we get the energy out? This is only conduction. So let's also develop some scenario where we have water flowing, and artificially we may assume the question is, how much would be the specific discharge from both sides in order to reach the same power, thermal power. And this means you set up the equation like this, and same result means essentially synthetically taking the same Peckley number. And the cool news is it's just very low discharge that is needed. Or in other words, this example is intended to demonstrate how inefficient actually conduction is and how efficient it could be if you have water circulating in the ground. And of course, when we engineer and we want to extract energy from the ground, the big issue is always, in my opinion, is water, artificially circulate water or groundwater. Well, independent of this, I'm focusing on groundwater. I'm focusing not on power generation, mostly on thermal conditions. And by looking at the thermal conditions and trying to understand why the thermal conditions are as they are, we ask in the second place, how much energy is there in, what is the geothermal potential? But in the shallow ground, usually we do not produce heat, power or electricity. We usually just use the ground for heating, cooling, maybe storage. Next kind of exercise. As I told you, I'm trying to look at the ground surface and how the ground surface thermal conditions influence the deeper ground. This is a cross section, and if you look up what you learned once upon a time, there's a geothermal gradient, right? So this is a thermal gradient which we need in order to describe this system with respect to conduction and how much heat flux is coming from the interior of the Earth through the crust towards the surface. And if you look up recent literature, you find some average value which is 87 milliwatt per square meter. Is that a lot? Doesn't feel like a lot. It's not so much. We can calculate values. For example, what is the net power output of the Earth? Something to the power of 13. And still, this is not so much fundamental information, but I find it interesting to compare this value to how much humans consume according to values by the International Energy Agency. We humans consume, according to their numbers, this here. If we calculate the energy which comes from the interior of the Earth per year, we have the same order of magnitude of energy that we all need as humans. It's a little bit less, so maybe 40%, but it's more actually what we consume than the Earth releases on the continents. That's impressive, isn't it? To me, I tried a little bit around, and I was testing several times. I hope there's no mistake here, but I find this here, I find this pretty remarkable. What does it show us? Maybe on the one side it shows us that we are consuming too much energy. On the other side, maybe shows that our motor, our engine Earth is not very efficient in releasing heat. Next question is, does it release this heat? Well, I found this here on the web. It compares how much the energy, how much the energy inputs are to our Earth's climate system. Let's trust these values, but the values are not so important. It's the relative shape of these cubes here, which are used for illustration. And of course, we know this, all the atmospheric temperatures, all our weather, our major engine is not the Earth, it's the sun. So solar radiation brings us the energy in, makes the warm and the ocean warm. There's an increase here, a contribution by global warming, which I find significant according to these cubes. And it's not so much the focus here, it's actually the major focus that I am interested in is the energy flow from the Earth and how much that is in comparison. It's not very much. So once again, proof of what we know already, the contribution by the Earth is not really very much. But still, the big question is, does the Earth really release heat? What do you think? You learned this in school, no? We have a geothermal gradient, we have heat flux towards the bottom. So, this is what recently has been the focus of colleagues a lot. I mean, not recently in the last years, but more and more things are condensed and more, I would say, also reliable, because this is known now for a long time. I mean, we have global warming, we all know this. As a consequence of global warming and having very inefficient heat release from the Earth, the atmosphere, as we know, is warming up. And what is the consequence? There's an instability. There's like all this kind of transient, very, at the ground surface, very boring coupling actually is out of balance. And as a consequence, this is the, I think, cumulative heat gain of the Earth as a consequence of global warming. So in other words, at the ground surface, 6% of all that global warming energy of the globe is is actually in land, in continental mass. Most of it, of course, is in the ocean, and very little in the atmosphere. And as a consequence, I like this work here, because of course this is also relevant for hydrogeologists and those people which are interested in the implications of thermal changes in the shallow ground. You see a list of many things which are relevant here as a consequence. And I guess if I would ask you shortly, look at all these points, is there anything that relates to you or to your work specifically, or do you see something missing or something wrong? Well, I'm fishing. I like this. I would say it's sometimes even good if the water is warmer. So it's not always bad if there is an increase in temperatures. But I guess this is certainly not complete. But it's nice how to summarize things, these many different trends. It's not just the atmosphere becoming warmer. There's so many effects we have also in the subsurface. And finally, coming back to this source of information and related work here by the colleagues, this is the ground heat flux history on the average for land on the Earth. It's a big range of in different methods how they calculate that. And at the end, for the recent years, we have always an increasing ground heat flux towards the bottom. So this is what they say, and this is what we know. How does it link to each other? How do we get the energy in here if we have this geothermal gradient? How does it does not fit, no? Because this tells us heat flux is in this direction. This tells us the ground is gaining heat. I would say not everywhere. Things are very non-uniform, but this is the average. So how does it work? Is it special physics? Well, surprise, surprise, of course, things are not that simple anymore. There is heat flux from the crust, from the interior of the Earth, and there's heat flux from the ground surface. As a consequence, we have gradients in both directions. The entire system is transient. It's on the way to get into some new equilibrium once our global warming stops. And of course, this takes time. And if you look at that, we can even specify some inflection point. So some point where temperature, the gradient is zero, so no flux upwards or downwards. So how would you, if you would be a hydrogeologist, how would you try to measure this? And how to prove that? What would be your proposal? As a consequence, just to illustrate that, if you take temperature profiles, of course they change in time. So on the other side also temperature trends of long-term recorded temperature in groundwater, they are also, according to this hypothesis, they have to increase. These two figures essentially lead us to the approaches we can use to confirm that there is a warming of the groundwater, and I show you this shortly. The implications that we have, just to summarize once again and pick those relevant issues that we found on these many impacts that could happen as a consequence of warming. We have, of course, enhanced geothermal opportunities because higher temperatures in the ground, in the top 100, maybe 200 meters, higher temperatures mean more efficient heat exchange, or in other words, we can operate our shallow geothermal applications in a more efficient way. I hope you're a little bit familiar with shallow geothermal application. Most standard one is the one that you see here, which is essentially bore heat exchanger, where we have a borehole drilled at a depth of 100 or 200 meters. And then it's equipped with a tube, and in the tube you circulate a heat carrier fluid, and above ground you have a heat pump, which is then supplied with the heat. Sometimes you have many of these ball heat exchangers, then you have a ball heat exchanger field. In Europe, how many of these applications are operated? What do you think? Your guess?
100. Tens of thousands.
Kino. Tens of thousands. It's, I think, reaching 2 million. And I'm always told this is super simple, and it's in practice. There's so much experience. There's not so much science involved anymore. I also like working on these systems. But essentially, this is an established technology which does not need any subsidies. It works. And of course, it works better the higher the temperature is for extracting heat. But on the other side, can also be used for dumping heat or for cooling. And of course, these kind of applications are, a little bit not so efficient anymore. We have also, just to summarize that, if groundwater temperatures increase, microbial activity is also increasing, oxygen depletion is enhanced, and redox conditions will change. Said negative, it is negative especially for animals and fauna, which is the subterranean fauna which lives in groundwater, which is sometimes a very relevant community, and this is also a focus of some studies, and I will come back to that later. And of course, if temperatures are changing a lot, there may be significant chemical leaching, and Kino, you mentioned that arsenic may be an issue, but I guess temperature ranges that you're dealing with are much more than these little few degrees that we have due to climate warming, global warming. And finally, of course, any kind of hydraulic connection that groundwater bodies have with surface water bodies are relevant. Many animals, many ecosystems are used to pretty stable thermal conditions, and if there's a change, this may be very critical also for example, groundwater-fed refuges. As I told you, let's now look a little bit into the ground. Let's look at measurements, and I have to say most of the work I'm showing here is descriptive. It's more like look, see, interpret, and we have a couple of studies done in the past and would like to report a little bit on these. So the good thing about temperature measurements is they're not very complicated to obtain, but there are also many existing already, and not just from nowadays, but since a long time. Many countries, many authorities run official programs, share the information. There are monitoring programs where temperature is often a side dish, just also collected, and I guess many of you have temperature testings, measurements somewhere as part of their business. And for us, we exclusively look at the temperatures and make things as much as possible simple. Here, for example, we had the chance to collect temperature from, I think totally it has been 40,000 wells. At the end, we chose 12,000 in 10 Central European countries, so no measurement done by ourselves, and try to average everything. So in a depth of something like 60 meter maximum, the measurement techniques have been different, so there's a lot of noise in this data, but overall, and also averaged over some time period, you see like what you expect. The temperatures in the shallow ground, they follow, maybe a little bit dampened, maybe a little bit shifted, they follow the temperatures in the atmosphere. Okay, so what we have been looking at, first place, has been in Bavaria, where I am from originally. And why did we focus on this? We have been lucky that in Bavaria, the survey collected temperature profiles in the 90s. And independent of the colors, which is the geology, these are the locations of all these wells, which are not used, but really just used for observations. And we detected them, and we said, okay, perfect. Now, 25 years later, 2019, every season, so 4 times a year, sent out the students and they have been measuring at these locations. So this is how fieldwork looks like in Bavaria, and good mood. Temperature measurement is nice and fun. And what we are interested in is so simple. We try to figure out if we have a profile of a temperature, does it change? And we tested something like 40 wells. Something like, I think, 10 of those have not been really reliable because we saw influence at great depth, so like in 30 meters during the seasons, temperatures are fluctuating. It's always a signal that it's not just heat conduction from the surface which plays a role here. So we have been really focusing on those wells which seem to be reliable. And these 32 good wells provided us with relative changes in the temperatures, which are shown here as these gray colored lines here. And okay, each well tells an individual story, and you could spend a lot of time interpreting temperature profiles. By the way, it can be really nice and fun, but of course, for doing this, you need much more insight in the local hydrogeology. We didn't spend so much time on this. We did just like a comparison, and the comparison ended up in a median of change, and only in one well the temperature did not increase. We don't know why yet. Maybe it's a good master study for the future, but finally, like a textbook example, temperatures increase, and if you compare what is measured in the state in the atmosphere, this is the temperature in the atmosphere at the local stations. This is how the groundwater responds to these temperature changes. Once again, this is due to averaging over all of these different measurement points. Yes?
How do you avoid mixing in the well because it's open?
Usually,
convection.
Yeah, I mean that's a permanent question. Or can you trust the temperature profiles? During the measurements, we measure up and down, and by this we see if there is any mixing during the measurement. Usually it does not happen, or there is very little. Usually we try to use those wells which are not too big, so which are small. And I have to be honest, usually we have some error also due to the vertical free convection, but we kind of ignore it. Okay, but there's a lot of uncertainty in this, and I would say trust big data, but of course don't. If you look at the single trends here, it's so different, and I mean that's why I think our science is so nice, because every well tells its own story. But for us, we want to publish papers. We want to see the trends that you expect. This is proof of concept perfect, and actually the Bavarian news, they grabbed this and it was in all newspapers. Wow, groundwater is increasing. The temperature in groundwater is increasing. What a surprise. Kino?
Are all of these wells not anthropically impacted? Are you sure that
That's a good question. The anthropogenic impact. The anthropogenic impact is actually a little bit coming later, the direct anthropogenic impact. But we, and you've seen that in those figures, we try to choose those which are at first sight not. And we drop those which obviously have some weird impact which you could not interpret. But this here, I would say the anthropogenic impact is not significant. So this is really what we expect to be due to the atmospheric impacts. Well, as another way of looking at these trends, as I promised, we cannot just look at the profiles. We can look at temperature trends. And temperature trends is not something you ask like students to go out and measure. This is something you find in long-term recorded data, that is recorded, for example, by local authorities. And one country which does that in a very good way is Austria. And in Austria, there are many stations, and cannot believe, but more than 1,000 wells they have permanent logging, not just of temperature, also groundwater quality in different ways. Finally, we find some, without going into details, we looked at something like 200 wells, which had time series that go back many, many decades. And we need decades. Why? Because the warming is nothing that you see just within 1 year. You need many, many years. And once again, there's a big fluctuation. And what we expect is that the groundwater temperatures increase. And we also have local stations where we can compare with the atmospheric temperatures. And at first sight, looks like as we expect, groundwater temperatures, the blue ones, big fluctuations, they increase. What a surprise. Similar rate as in the close by Bavaria. And the atmospheric temperatures also increase. What is different? What is different? Obviously.
It's more steady.
I think it's due to averaging. It's not steady. I mean, the difference is actually previously in the other slide, the air temperatures have been higher. And here the groundwater temperatures are higher. How can that be? Kino, thank you for your question. This is obviously there are other impacts. And a major reason here is that humans, which usually live close to observation wells, they obviously also enhance these heating of the subsurface. An interesting thing, and where do most of the people live? In cities. And this is why I will extra spend some time also on urban environments. Before that, I would like to proudly present some more recent work we published, because if we have so much data, at least in Europe, I have to admit, not any in Africa, but we have colleagues here and there, and we teamed up with Australian colleagues and from Canada and try to do what you can do when you have a lot of data and you have many information of colleagues on land cover, on temperature trends on the ground surface. What else do you have? You have global lithological maps or soil maps. You have global databases on heat flux or geothermal gradients. So it seems like you have all the ingredients you need in order to cook a global groundwater temperature map. And what you can even do is you can use climate models to predict how the groundwater temperature evolve in the subsurface. So this is something that leads us to what is shown here, and it's also here like on some Google platform where you can use if you're interested in, and it shows how the temperatures would change if climate change would just continue according to the expectations we have nowadays to 2100. And it's not so visible here, but in this kind of game here, or this exercise, you can see on the left side what our interpolated temperatures are in the groundwater table. And this is how the temperatures would evolve, and they would of course increase in the shallow groundwater on the long term. In order to calculate that, as I said, we rely on data on geothermal gradients. We can calculate the thermal diffusivity roughly with some assumptions, and I guess not all are correct, but on the average they may be sufficient. We can use global climate models and look back by looking at existing data, for example, of either land data, which I think goes back to 1980 on the global ground surface temperatures, which we need as input to calculate in a 1D the heat diffusion into the ground. Bernard?
Just on your last map that you showed, how do you know the temperature of the groundwater when you don't, so well spatially, when you don't know the water table position?
Well, there are also maps on the water table. And there's a good question.
How good are these maps?
Excuse me?
How good are these maps?
No, they're not good. The piece is published now. I think we have one colleague which published groundwater tables globally in Science, which is also attending this class, no?
She didn't directly.
So ask her. But, I mean, come on, we are all, let's be honest. On this scale, if you grew up in in local groundwater watersheds or groundwater studies like myself, of course you're pretty skeptical about local results, and just when you go back to that kind of online feature to check with what the groundwater temperatures are, I wouldn't trust them. But the big picture, of course, is something that we're interested in. This is something we want to show.
Getting back to something that you showed at the very beginning, how important do you think thermal diffusion is versus recharge ejection?
I will elaborate on this, and it's obvious it's something that should be also considered, because we have recharge, and as consequence of due to groundwater recharge we have advection that plays a role, and we did some testing, so thanks for asking. But of course gives us a hard time, because a lot of complexity comes in when we have to not just when we have to also consider recharge, which is difficult not by values but to implement as an additional heat flux component. Before coming to that, just very shortly to summarize, this is the equation, and the equation is formulated in a way that it shows how it's applied. It's superimposing every time step, so each time step it's on a monthly basis. We can calculate the temperatures, and in this case it's on a resolution of 5 kilometers. And we have the temperatures, we have the time, of course, the time steps, we have the depth, we just are interested in the top 100 meters, thermal gradients and thermal diffusivities, and no fluid flow. And finally, if we look at different locations, this is how the results look like. I haven't mentioned this, but I think we're all aware of this, that close to the surface we have a strong coupling on a seasonal scale with the atmosphere. But in the depth of something like 10, 15 meters, you don't see so much anymore of this. At least if you only have diffusion. Big question is now, how about recharge, and if advection plays a role? It gave us a hard time, because most of the people in borehole climatology, so we're not the first one looking at such things, they are also asked the same questions, and people are then interested in dry boreholes, not so much water, make sure that no water is flowing. We tried a little bit, and there's an average recharge value globally which is in this range. I know, at least in the regions where I grew up, these values are much higher. Okay, but it's a global study, and with this global study, and if you look at the settings here, with a 2D model with some vertical watershed, some water circulation, we have obviously a vector of heat flux towards the subsurface. The big question is, how does it change? We have here 3 positions. How does it change when we include this in comparison to just considering conduction? And the good news for us is, if we look at this here, this is kind of the error for these different positions. The error is very, very low. And the major reason is, it looks at first sight, there's a lot of advection going on, but the major direction of advection is horizontal. So water gets into the subsurface, and you look into the water circulation, usually assumed as it is in the shallow ground. Most of the water actually does not flow along the thermal gradients. Just by Peckley number, we are in a diffusion-dominated condition, but clearly, if you consider much higher recharge rates, this may play a role, but we didn't elaborate further on this. And in a way, trust that actually other aspects are more important, for example, how you initiate your model and these kind of things. And also thermal diffusivity may play a role if you take different values, just examples. This is how the accuracy of these assumptions are. But at the end, It's by the procedure extremely simple. It's of course for the purpose of publishing something in Nature Geoscience. And finally, we have been, I think, in a way also happy that we saw there's no calibration with all the data that we had on temperatures, and we compared them with the temperatures that we produced. It's pretty decent, it's pretty okay if you compare with the accuracy of other global models. And then you can produce these maps which show you how the temperatures are at the water table at different depths and how they evolve in time. And in 2100, surprise, surprise, everything is increasing, temperature getting much higher, and everything is getting red. So that's not so surprising. Big question is, what else can we find here? Interesting is once again this inflection point. It's interesting at first sight, but at second sight it's also trivial because it propagates further down. So most important is of course the implication. And without discussing in detail what it means in terms of geothermal efficiency, as I mentioned before, high temperatures are favoring better geothermal energy extraction for being used for heating. On the other side, if you use the ground for cooling, and this is more and more an issue in many places, of course this is critical. If you think of groundwater temperature thresholds, and there are many different values which you find, what is the right groundwater temperature threshold if you would like to use the groundwater as a freshwater resource? You find values like 15 degrees, 25 or 34. And we all know that many groundwater natural conditions are already like in some high ranges. But of course these high ranges are getting more and more, and if you calculate how many people are living in these areas which are threatened by too high groundwater temperatures, of course the number of people is increasing without knowing how the number of people is increasing at all. Just to pinpoint one special aspect which I mentioned initially, the groundwater-dependent ecosystem. There has been a study on thermal refugia mapping in the US, and it was found that at 40% of these more than 1,000 stream sites, we have groundwater-dominated conditions. Usually groundwater releases cold water in some streams, and these are the areas where fish are breeding, where special ecosystems are used to very stable conditions, and these areas are refugias. So I'm not an ecologist, but obviously if these exist, it's very easy to calculate how many are threatened and to what extent the temperatures are increasing. And surprise, surprise, everything is getting red on the very long run. And I mean, if the organisms here, all the species here are used to very low temperatures, and especially to stable temperatures, this may be a very critical aspect. Coming back to fishing, okay, maybe not good for fishing. All right.
Quick question. At high elevations in the northwest, we actually see ground temperatures sometimes going down in the winter because lack of snow cover, and so we have more long-wave radiation. And so have you considered the impact of elevation on these results?
We did a previous study, also looked at elevation, which was not so important as, for example, when you want to look at different factors which you would include to predict the groundwater temperatures. Much more important would be, so for example, to correlate your temperatures with nighttime lights because of humans. And by the way, I have not shown this or stressed this, all what I showed here is not for permafrost areas, and I would not trust in high mountain areas either. So
Yeah, and there's no wells up there.
no, but yeah. Okay. I mean, I personally, as I said, I'm a hydrogeologist, and this is my major focus area. But I'm lucky that I have PhD students and especially collaborators. And just to mention that, we teamed up now, and since a couple of years, we look at the thermal conditions in the ground and how they interact with the species which are found there in the groundwater. Is there anybody here who works on groundwater ecosystems? Nobody? A little bit? It seems to me like not so many people, but there are specialists out there, and I have colleagues here in Vienna, for example, which are really very good, and they tell me what the names, which I cannot pronounce, of these different animals. So there is, of course, only where you find oxygen in fresh groundwater, there are enormous ecosystems existing, and in a way during previous times they have been a little bit ignored. Nowadays they are considered as a major argument why nowadays regulators say we have to set thresholds for temperature when people want to use the groundwater. Kino, what is the temperature threshold in Switzerland?
Average 50 degrees.
50? No, the threshold.
The threshold now is 3 degrees, 100 meters downstream of the facility.
Why 3 degrees? And you mentioned that, why it is like this?
I mean, because you can change the microbial community if you go higher temperatures.
With 3 degrees, but it could be 5. It could be 10. Well, the big question is, what is the right value? And this right value is not existing. Everybody imposes some value. We are aware of these ecosystems, that they exist, but there's little knowledge actually how sensitive they are.
I'm sorry, Peter. I think that this fauna only exists in alluvial aquifers, in cars.
No.
Yes. Look at the size of the scale that you have, 0.5 millimeter.
It's true. That's true.
I mean, if we go to a sandstone, you don't have these pores.
For whatever reason, you find these animals there. So it's true if you have a sandstone which does not allow that, but it's not just the size they have, but they are flexible. They are completely adjusted to these environments. And finally, I have to be careful not saying things that I don't know. But finally, what is most important, at places where we are and where we use the groundwater, usually you have these pathways where also the animals have the pathways. So it's not just the alluvial aquifers somewhere in the mountainsides, it's many places. And I can tell you we do studies, especially in cities, mentioning that in the last part of this talk, where everywhere are these animals, even though people say there's no oxygen.
No, I mean, I don't disagree with this. Your statement is that this is particular for certain pore sizes. That's the only thing, you know. It's that we cannot say that we find this in every aquifer. We cannot generalize. That's my point.
I do not disagree. You're fully right. Yes, and it's.
That's my point. Of course, I have seen it with my own eyes. So I have colleagues that bring me to the field and they collect these amphipods, and it was fascinating.
Amphipods and others. And they collect it, by the way, like this. And this is one of our colleagues, Julia, which does it. Also fishing. So fishing is something I'm also doing in other ways. This is something very, very interesting. I mean, for me as a hydrogeologist working together with groundwater ecologists, this is like a review we try to do to summarize the knowledge in this respect and asking, is there for some of these species, is there already reported temperature sensitivity? And without going into details, the different bars show increasing temperature sensitivity. Or in other words, how long they survive. And obviously those different ones which are illustrated here, they seem to be sensitive. This is, however, only lab studies. How much can you trust that? And in a way, I would also ask, how much is that relevant? If they have a little bit less lifetime, maybe the community diversifies, it's not an assessment of good or bad. And this is where, for me, I'm very, very limited in understanding actually how to assess that and to say, is it good, is it bad, is 3 Kelvin, for example, justified? I personally believe not. But when it comes to temperature, it's actually not just the temperature which directly influences these animals, because oxygen solubility decreases a little bit with increasing temperatures. The major point is actually that the microbial activities are enhanced, and as a consequence, the oxygen disappears, and then they should have bad living conditions. This leads me now more and more towards the extreme values here. Nobody has actually mentioned. It's obvious that these are not existing at first sight, according to our knowledge. They are existing, and especially high ones. And why? Because they are hot springs, and they're also part of this, but this is not the focus here. But some values are really high. And what we did, it's very simple. Look at what is happening at these very high temperature wells. And you find, if you look in Google Maps, you find everywhere, nearly all of the places, you see industry, automotive tracks, I don't know which one it is, and especially cities. So urbanized areas, you have this, what you mentioned before, what we saw also in previous temperature trends, we see a direct impact by humans. So obviously we have the climate change, we have global warming, which impacts the thermal regime, and at the same time, especially where humans are, the temperatures are getting warmer and much more than in natural environments. We can summarize things and by the question of what is the size, if it's linear, polygonal, or if there are direct geochemical sources, which of course are also existing, and this is really a very strong heat release. But when we talk about cities, in cities where we don't have geochemical reactions, but we have other sources, we have obviously enhanced heat flux into the subsurface. And as an example, Kino, that's why I was asking you, because we share we shared some time in Zurich, and in Zurich there is a parkhouse Urania, which is an underground car park. And it's one of these unique ones. It's not just, I was told, the most expensive one in the world. But when you enter it, it's in the very center, you find this here, and these are actually wells. And don't ask me why somebody put a well in the center of a car park. But it's, for us, it was like a dream. It was a dream, and it's not just ending in 2006. Do you know it, Kino? This Urania, do you know it? No.
Yeah, that's why they have waterfalls inside of the parking.
Yeah, well, and if you talk to the local water authorities that you want to test it, they feel like we all come and watch us. There's still a sensor here installed. But, I mean, it's not ending in 2016, but I'm showing this here because this is kind of a perfect sensor to see how this parking, underground car park, so obviously infrastructure that could be an enhanced heat source, influences the subsurface. I'm showing that because it's not just the most expensive one, but it seems like also one of the hottest ones. If you look at the temperatures here, they are very high. They are in Zurich, what would you expect? Anybody?
I just say the temperature of the aquifer.
Well, natural environmental temperature without any direct human impact, I would expect something like 11 degrees or so. Well, if you look at that, we're reaching 20 degrees and more. So obviously, our Urania car park is illegal. No, I mean, we have in cities many influences. It's not just the car parks, which is so nice to show. In cities, we can look once again at the large scale, and we did that for some time. We tried to categorize different factors. It seems like the buildings are playing a big role because they release heat into the ground. We have paved ground, which accelerates the heat flux. We know that in summertime, They're much warmer, a few degrees warmer actually than the green spaces. There's also infrastructure in the ground that releases heat. And it's not just the district heating networks which may release some heat, but also sewage systems or underground tunnels. Of course, cities are super complex if you want to resolve them in 3D. And we try to keep it as simple as possible, always thinking of a kind of two-dimensional or one-dimensional cross-section through cities. So apologize for this. And it's not a subject we're working on alone. Others are also working on that. For example, in Japan, in Berlin, Winnipeg, colleagues have been measuring and looking at the temperature profiles which have been recorded. And as we expect, we find always this kind of bending here, this C-shape due to climate change. If you look again, it's not just climate change, it's too much energy. Temperatures are too high, so we have a superpositioning of urban heat islands in the atmosphere of global warming, and of course all the additional heat released in the subsurface. If you look at that, it seems like our cities could be the lab for the temperatures we find in the groundwaters in the future. No? Well, and also here in comparison some real profiles. Okay, what's this? So I want to show you a little bit how we tried to calculate. Yes?
Since most of our energy is coming from the sun, why is it not in the cities where we have those skyscrapers that we have more shadows, and that's why we don't offset some of this anthropological footprint? Because the asphalt absorbs much more heat and releases it in the ground, and it re-radiates. And we don't have evaporation, for example, which also consumes heat. So in cities, this is a different story, but it's known since 100 years, and everybody of us knows it. In cities, it tends to be warmer. It's called urban heat island. We here talk about subsurface urban heat islands. Subsurface urban heat islands obviously are more intense, have on the average higher temperatures than those temperatures in the atmosphere. And as I said, the reason is there are many sources at the same time that superimpose, which permanently release heat into the ground, and the heat is stored in the ground because the heat transport processes are not very efficient. And as I said, we try to keep things simple. And for example, we could, and we did that, look at a city like we did it for Cologne in Germany, and we looked at how is the building density, assuming that each building has a basement, very roughly, and the basement of these buildings has some temperature. And then we can do a 1D steady state assumption. We could collect many temperatures in the groundwater, so we have a temperature profile, and we could interpolate that and then ask ourselves, so how much is the heat flux into the ground from basements? If you assume some average value, which is given by civil engineers, and should be something like from the basements, something like maybe 17 or 18 degrees Celsius, or 17. And we come up with values for the city. In this case, it was Cologne, I think, which is 282 watts per square meter. And this is much more. It's an order of magnitude higher than we had previously for natural environments. So let's have a closer look. And I'm accelerating a little bit. Two cities in comparison. One is Cologne, one is Karlsruhe. Once again, remember we have been in the tens or 100 milliwatt range. Here we are in hundreds of milliwatt range of heat released into the ground. This is how it looks like when you can resolve the buildings in the city and where we have built up areas. These blue areas here correspond to green spaces, and according to these gradients, it seems like there's a little bit of heat release also from the ground in the green spaces. And these are subways or so. Finally, if you look at our profile, there's even more heat accumulating in the ground. Colleagues have been looking at that in different cities. Meanwhile, and big question is not just how does it look like, or people look also in different ways, maybe with different methods. The groundwater conditions and the level of the groundwater is different, so not everything can be compared. But if you just look at this kind of summary here, many and nearly everywhere we see the same conditions in the world. The temperature seemed to increase much more than in the environmental undisturbed conditions, and for Cologne we tried to look a little bit deeper. It was a hard work for Hannes, which is one of my colleagues in our group. And in Cologne, the good thing is there's been a lot of water management for a long, long time, since the 1960s. This is, of course, great. It's like a treasure to look for the thermal trends in the long run. Of course, the big problem is the data is so diverse, the measurement techniques are so diverse, bringing everything together is pretty difficult. Gave him a hard time, and you see how profiles looked like, and how the loggers, the temperature loggers, provided information. He tried to compare to local ground temperature stations, and with all these dots you see here in the background, you see the ranges of groundwater temperatures in comparison to this air temperature 2 meters above ground, which is blue. So much higher temperatures, and surprise, surprise, temperatures are increasing. These are measurement campaigns we did, and this is where I was born. And just because finally we are also here a little bit happy how things are looking like. This is the left side of Cologne. This is the Cologne Cathedral. This is where it is. And if you look how things are evolving according to these measurements, we can look at that in space and time. Just at the center where the cathedral is, seems like temperatures are increasing the most. Okay, and yes, please.
Have any of these example study areas that are having temperature data over all of these years, have any of them also been taking water quality measurements throughout?
Yes.
Are you going to show any of that? Okay. So then my next question is, because I'm curious how it would change the water quality, but also how would you be able to relate it specifically to temperature and not other contamination or something?
Well, first of all, I'm not an expert. Second, it's so much work with the temperature, I guess, with the groundwater quality. And third, do you know anybody who has some time? I mean, this is super interesting. Of course, that's the nice thing about this. Temperature is usually not the first thing people look at. They collect it as part of groundwater quality programs. And I would even believe it's not just taken for being taken, that others have already considered trends and changes, but maybe they have not related it to the temperature changes. I mean, I do not dare to give a correct answer on this, but I think it's nice to show how things are evolving. This is Cologne. Finally, for Cologne, it's always the same story. You see these temperature profiles. By the way, for the students, at least if I were a student, I would like the job, traveling in a city and taking measurements everywhere. We did that many seasons in Cologne for many times. Finally, like the last part now, and I'm finishing, big question is how is if that is happening, it's good for us. Why is it good for us? Because we have increased geothermal potential. Is it beneficial in terms of can we use that? Can we see that? Can we assess that? I mean, there's a lot of heat in place in the ground, which is the theoretical potential. You can calculate some technical potential by looking how you would distribute geothermal applications in a city, which is also a very tedious job. You can roughly estimate it, and so many people did it in many different ways. We tried to see in Cologne how the heat flux into the ground and the temperatures are changing on the long run, once again also with respect here to the available energy. It seems like most of the energy has been accumulated already in the past, and nowadays we still have heat that gets into the ground, but the temperatures do not change so much anymore. It seems like this subsurface urban heat island is evolving. It's not so much changing in entire intensity, and heat gets in and water flows and water also takes it out. So actually next step obviously has to be a numerical model, but also this is something takes time and it's not done, and we have not done it.
No question. Maybe this is more of an engineering question, and I'm not sure if the rise in the groundwater temperature is enough to do this, but I'm wondering if it could like start damaging infrastructure because of expansion or contraction or something like that?
Actually, there's a study of a colleague from the US which focuses on this, but I don't know exactly the reference, but I can give it to you. We have not worked on this. And I think, in my opinion, it's really only relevant if you have clay environment, and usually if you have clay, you don't have so much groundwater. So this is where things could be problematic, but you need also really significant changes. Once again, we have significant changes in the subsurface temperatures beneath cities. And kind of one of my last slides, I want to show you, many are looking at the question, how is the geothermal potential in cities? And without going into details, the question is how much of the heat demand in a city could be supplied by the heat which is in the ground, and you can compare the need for heat to the available heat. You can compare it to the technically extractable heat. You can compare it to the renewable heat and so on. And as a consequence, nowadays there's no common sense how to assess that, and this is how results look like for different cities, different ranges. If cities like Beijing exist, where also obviously these heat islands in the subsurface are existing, the reason it's so on top here is because the heat demand is not so high. But very roughly you can say that the heat demand in cities maybe by 10-20% certainly can be supplied by geothermal sources without any doubt. And just to motivate that a little bit further is my, I think, last slide now. This is a study that refers to the so-called power density, and it shows comparison of many different sources for energy, not just heat, but also for power. And I find it remarkable to emphasize once again here at the end how much energy actually is there in the ground. And if you are able to extract it, we are competing here with the most established and most attractive renewable energy technologies. So let's go for it. And I'm done for it. These are all the co-authors. Should most of the work. Thank you very much for this, and thank you very much for your attention.
We have time for 10 minutes of questions, so have at it.
Kino.
Thanks, Peter, for the very cool presentation. One of the main issues that is now on the table is that the household facilities that usually they are open, they only extract heat. Do you think that this release of heat or loss of heat from the cities can counterbalance the extraction? Because in cities like Winterthur, they are afraid that they will cool down the aquifer by the fact that they will extract heat continuously. But I mean, according to what you show here, there is a release from the basement of the foundation of the buildings, etc. So do you think that one can counterbalance the other? There is no risk to cool down the aquifer?
It's obvious that the example that you mentioned, the examples that I have shown, you have to bring in together thermal management or heat supply management in, I wouldn't say in a city, but in districts, together with the available heat in the subsurface. I think, I mean, depending where you are, things are already very well developed. I'm thinking of the Netherlands, where they're doing a lot of heat storage, which is not just something you do at some local space, but has to be arranged. In Zurich, in the Limmat Valley, the city runs an own numerical model in order to see how the different groundwater applications interact. And in Basel, another city in Switzerland, I remember colleagues always stressing, actually in cities, at least in these climates here in Central Europe, they are not actually struggling with heat or temperature decline due to heat extraction. On the average, in the future, it seems like the cooling is the greatest problem. And especially because in many cities, bigger buildings, they do not need so much heat, and they need more and more, because they're well insulated and well thought. And at first place, you think of the heat supply. In the second side, where do I get rid of heat in the summer? We dump it in the ground. And in Basel, there's a lot of industry. These are great sources, and they have trouble to struggle with this. And I believe it's something, depending where you are, much more relevant in the future. It means essentially heating and cooling, using both sources in a very strategic way, of course, is the best way. Has nothing to do actually with the urban heat island effect. It's just on top of this.
I have a second point.
Yes.
I will shut up. So, in order to define a law that put a threshold of temperature to maximize the use of geothermal energy, because if you don't allow, at the end you don't get anything from there, and if you don't put threshold, people will overexploit. I mean, we are encountering a lot of difficulties to define the mean temperature of the Earth. Do you thought about this? It sounds like a trivial problem, but it's not.
Of course not.
And you need to, based on the mean temperature, you define a threshold, and then you say if low above that, they will not impact in the hydrochemistry, microbiology.
Kino,
Something about that?
My thought about this is it's great that it's like this, because this is nature, and it's not so simple to say 3 Kelvin and please abide this. We need solutions which deal with the natural conditions, which are transient, and which there is no magic 1 or 3 Kelvin or whatsoever which is applicable. In my opinion, I mean, we drive cars and we breathe the air. Old-fashioned cars. It's not. I'm a hydrogeologist, and I feel also like an environmental scientist, but I believe we should consider many areas in the subsurface which should be at first place not freshwater resources, but energy resources. And no matter who and what is actually happening there, living there, and what is happening there, we have to, not just always, first of all, save the water, but we should try. And finally, I'm also told by colleagues who are more expert in ecosystem research that actually the steep gradients are often the interesting ones for biodiversity. Maybe we are overlooking things here, but I'm more reproducing what I think, but not what I know.
So you showed in a few slides in your presentation temperatures in the ground, the subsurface, rivaling increases in temperature in the atmosphere.
Yes.
How is that possible? I pictured air heating up much faster than rock. And in cone, for example, increases in temperature seem to be rivaling average increases in climate.
I mean, I hope I understood this question correctly. I mean, you mean these areas in Cologne where we see that heat comes from the subsurface? You mean this?
Well, you have average ground temperatures,
okay,
surface ground temperatures, which are 1.5 degrees Celsius. But from climate change, average atmospheric temperatures are increasing somewhere between 1 to 2 degrees Celsius. How is it that the ground is increasing in temperature as quickly as the atmosphere?
No, it does not as quickly as in the atmosphere. Maybe the best example actually is what I showed as the very first study case is where we saw the profiles, the average profiles, which are dampened in the subsurface. Everything is dampened. Everything is delayed. And the deeper you go, the less you see the consequence of surface effects, clearly. But, and I think that's important, even though heat diffusion is very slow, it's sufficiently fast that we can see climate change to a depth of 100 meters and more. And cities have their footprints also deeper than 100 meters already in the temperatures. You can calculate that because of the long time frames. Tens and not hundreds, but tens of years, decades, many decades, century of heat release locally. Maria?
In this paper, in the last paper of BENS, you checked also the threshold for the drinking water. Is it also very varying from one country to another,
Yes.
like for
Yes.
chlorobonation?
Yes. No, I don't know what the reason is. I mean, it makes sense that some countries which have naturally very high groundwater temperatures, they set different standards. But clearly, cold water is, I mean, better for us to drink, and it's getting critical the warmer it is. It's just thresholds which are existing, but I don't think they have too much meaning. At least for me. In practice, they have.
Yeah, so I was wondering about if we're doing heat extraction from the ground and cooling down it, we need the groundwater to help distribute it as well. Does that make a huge difference in affecting?
I mean, it's a good question. And why? Because the way we're looking at things is only with our boreholes or with our wells. And clearly, these are only the measurement points, and we only can interpolate. We do not see really a 3D picture. It's all what you saw is only interpolated data. But in a way, I think I would trust that, because locally we measure, but we know that the heat flux and the gradients are, most of the cases, mainly in the vertical direction. So I would say yes. Everywhere where we have local fluctuations in the groundwater temperatures, especially where we have river groundwater interactions, the story is always much different. On this global scale, it doesn't play a role. On a 5 kilometer scale, this average is off, doesn't play a role. So something is not relevant. But I mean, temperature is a tracer and is a marker, and something which is very relevant to see in many respects and to interpret, especially when we have very dynamic groundwater conditions, is an extra story. And clearly this is an issue, but it's not covered by these studies here.
Is there a map showing, at least for Europe, cooling and heating balance? Like, is there more of Europe need for cooling or for heating?
I'm not aware of this. Not on a European scale. I think they even have troubles in some cities to know who uses the heat in the ground. But would be interesting.
Students first.
At the beginning of the presentation, you mentioned that those are for like 2 million, I guess, ground source heat pump setups across Europe. Are they mostly closed loop systems?
Yes.
If they were to be standing column wells, how do you think that would impact the groundwater?
It's a mean question, because I'm not an expert in standing column wells. And standing column wells is a favorable subject in Canada, and you're from Canada. I don't know. I mean, by the energy balance, I would say it's the same.
It should be the same.
Yes.
Yeah.
A little bit difference, of course, is that, first of all, the standing column wells only make sense where you have aquifers, and the closed loop systems, they extract the heat not in first place from the aquifers, but from everywhere. So it's not something that you can immediately or easily replace. And on the other side, if you have water flowing, of course, the effects are not so local. They are like more regional.
What is column versus Fiona?
Like in a closed loop system, the entire well is cased, but then a standing column well, it's not cased. So you're taking groundwater directly and re-injecting it into the same well.
Maybe one more question.
Two more.
Or two.
But ladies first. Avra?
It's just a simple question. You did mention that at some point the ground temperature would reach a limit to start to equilibrate.
Yes.
And I would assume it's because of the capacity, and it will almost just start to go further.
Yes.
Does that give a sense of urgency, like to use that before reaching equilibrium break? Because it will be harder to actually extract the temperatures as it goes further, or does it not?
You may also argue that it's good that it goes further because then the battery is getting bigger.
That's true.
Two little things. First, we tend to focus on solar irradiation because it's the one that we're dramatically attached to. But long-wave radiation is very important. And long-wave radiation goes with the fourth power of temperature difference. And so this buffering that you're seeing in urban areas, would that be related to this fourth power term in the long-wave radiation, which is about 150 watts per square meter? And if so, can we calculate the equilibrium temperature change that we should expect?
I don't know. Well, I mean, that radiation is to the power 4, clearly. That's why it's so super dominating here in the atmosphere. And finally, I've not looked at any, let's say, coupled processes of how radiation at the ground surface interfaces with the conductive heat flux in the subsurface. But finally, I don't think it's relevant, at least for my studies, because we are in first place interested in the reciting temperatures that we have. And the reciting temperatures at the urban surfaces is not something we simulate, but the effect of these surfaces is the thing that we are interested in. This is our boundary. And by the way, it's actually the opposite boundary of people who look at urban heat islands in the atmosphere, because they do not look in any respect into the ground. Maybe that would be a nice interface of interdisciplinary research. And also these land heat flux studies that I mentioned in the beginning, they seem to become prominent more and more during the last years, because I think in the first IPCC reports, the land was this very small error, and nobody considered this, that this is also relevant because all heat is dumped in the ocean.
So second little point, if you go back a couple slides to your groundwater temperature box plots. So it's just a couple slides ago. One more. What I want students to think about
this
is,
one?
One more, the ones with that actual statistical bounds on them, on the temperatures measured, go back more, oh my goodness, it was a little more. There you are. Okay, so you said, surprise, surprise, it's warming up. But I want students to think about those box plots and think about, a lot of times in groundwater we forget about statistics. And so if you were to calculate the trend in those yellow box plots, the question is, I have for you, is that rigor, when you say it's warming, we could make, now because you have so much data, we can actually do a statistical hypothesis. Is it warming? Is it definitely warming?
Is it a question to the students? So we leave these questions for the coffee break, right? Thank you very much.